the question is, what is statistics, right? I mean, why do we even bother learning this subject? Well, think of statistics. Technically, it's said statistics is nothing but the science of data. And what does that mean? Well, what we are trying to do is make decisions based on data that we collect. Okay. We make decisions all the time. For example, if you're coming from, say, Hudson, you might figure out, what route should I take to come to Kent? Well, if you knew there was a traffic accident, then you would change the way you come. Why did you change it? Based on data, you made a different decision, what you thought was most effective. Many times when we are standing in grocery lines, you try to pick the queue that you think will get you the fastest through. But you know Murphy's Law, right? At least it's true for me, even though my name's not Murphy. Every time I stand in line, that's usually the longest, right? But that's what we try to do. Based on data, we try to make decisions. So what statistics is, it allows us, gives us tools by which we can study this data and come up with decisions. So think of this as data-driven decisions. Okay? Does it make sense? Does it make sense, for example, to have frequent preventive health care? Is it effective? Does it prevent more diseases? Is smoking causing cancer? All that is based on data. Okay? And that's what we're trying to do. Study a set of methods that allows us to look at data and figure out what kind of decisions we need to make. Okay? That's really what we are trying to do. So we're going to look at a few ways of collecting data. So what we're going to do is to take a look at ways of describing data. Look at the assumptions behind data collection and then ask the question, okay, so what does this mean? Okay, that's really what we are getting at. So descriptive statistics means we look at this data and describe it. And we're going to describe it in multiple ways. Why is that important? Suppose you walked out of the room and said, okay, describe your instructor. And you would probably start laughing crazily, but if you wanted to describe your instructor, what would you say? Under what dimensions can you describe your instructor? Yeah? Male, okay. What else? So if you go outside and say, my instructor is a male, that gives you a complete picture? No. What else? No hair, okay. What else? Yeah? Glasses. That means he's blind, okay. What else? Right now, all these are physical characteristics, yes. Mustache. Fake, okay. Funny, no comment. Yeah.
Wear a watch on your left wrist.
Oh, okay. I bought it in China. No, Rolex, no. Sorry. Bad joke. Okay. What else? Okay, so these are all physical characteristics. Right? I mean, if you go outside and describe all these physical characters, that's only one dimension of it. Does it give a complete picture of your instructor? No. So, humor would be more of a psychological characteristic. But there are other characteristics. So, would you agree with me? The more different dimensions you describe your instructor, the better the picture they get. So, if I am data, I wish I was as smart, but I'm not, for all you Trekkie fans, right? If I was data, and you were to describe me, and if you describe me in multiple different dimensions, then the picture you get of your instructor is more complete. You can make better judgment using that. Similarly, when we have a bunch of numbers on our screen, and we want to make sense out of it, what we're going to do is describe that data in multiple angles, multiple different dimensions. Okay. What we're going to look today is exactly that. Because why? The more we describe it from different viewpoints, the more complete picture I can get. When we use data and get something useful out of it, we say that's information. And when we have information and make some value out of it, it's called knowledge. Okay? So data is the first step. Next, it's information. Then make use of it. It's called knowledge. Okay, so what we are trying to do is go from data to information. That's what we are trying to do. So the first part is descriptive statistics. So this whole chapter is on descriptive. We then talk about inferential statistics. That means using one set of data to make inferences about another set of data. So for example, if I were to make inferences about how you would perform in this class, I could use your scores from previous semester and say, based on this is what you did in the previous semester, this is how you're likely to do here. That's inference. Okay, but we're not going to touch that in this chapter. So the first thing we do is when we have data, we need to actually go and collect it. There are different ways of collecting it using surveys, observations, and experiments. We're going to take a look at them. But just start off, okay? How many of you filled out a survey? Ever? Okay, so next question. Do you think the results from the survey are valid in some sense? Let me rephrase the question. When do you fill out a survey? Under what circumstances do you normally fill out a survey? Hey, exactly my viewpoint. Like my shirt? Yeah? Okay. So, you normally fill out a survey when either you feel a strong need for whatever the survey is asking for, or you have not done your laundry. Right? Basically, you fill out a survey under very special circumstances. You don't, how many of you very altruistically fill out every survey you get? Well, nobody. I don't expect anybody to raise their hand because that's what's true. So what does that tell you about survey results? They are essentially what we would call biased. Okay? That means survey results indicate an opinion about a group of people who either feel strongly for or against something. Okay? So usually survey results are not very useful, but we still do it because many times that's what we have to do. We will usually, if you want really unbiased results, do experiments. But experiments are really hard to do. And we'll talk about that when we come to that. So right now what we're going to assume is, okay, we have this data. How do we present it? So we're going to look at the presentation of data. And in the last part of the chapter, look at how we characterize the data. So let's talk about that. Data, when we describe data, we have to describe variables. Variables are what hold information. For example, I could describe a variable called name or age. And if I would look at him, the value of name, the variable name will have a particular value, and your name is Seth. Okay, his name is Seth. So the value of name has a particular value. And age will again have a particular value. So those are variables. Now, variables fall into one of two categories. Variables that we say are categorical and variables that we say are quantitative. Age is a quantitative variable. Why is it quantitative? Because the value is expressed in numbers and we can manipulate the numbers. So, for example, if he and I went out and we say, what is your average age? I would say about 60, given that I was 110 and he's only 40. No. Right? I can manipulate that value. Age can be manipulated. So values that can be manipulated, you can take an average, you can take the highest number or the smallest number. Those are values which are quantitative. But with name, we can't do addition of names. Can I take Seth and Murli and add them up? I don't know, we could probably get confusion, but we can't add them. We can't manipulate those values. So values that cannot be manipulated, which are basically classes or categories, are categorical variables, or the other word for categorical variables are qualitative variables. Okay, so quantitative variables are variables which have numbers which can be manipulated. Qualitative variables are basically classes. Now you've got to think carefully. I can divide this class into two groups, males and females. I can also divide this class into two groups where I represent males by zeros and females by 1. My question to you is, if I designate the class as 0 and 1, where 0 means males and 1 as females, is that variable quantitative or categorical? Categorical. Just because I said 0 and 1, that means you can't take an average. Okay, so it's still categorical because even though it's a number, you can't manipulate that value. Okay, so we're going to have two types of variables. Categorical variables, we're going to represent it graphically by two things, bar charts and pie graphs. Okay, both of them are for categorical. For quantitative variables, we have multiple. Histograms is going to be the most common way of representing quantitative variables. We'll also look at stemplots, but stemplots are going out of favor because we have access to very good software which allows us to get a more complete picture. Okay, so but we'll still look at stemplots. Okay, so I want to collect data, and let's say I'm interested in collecting data about this class. What is something interesting I can collect about this class? What do you think I should know about you? Or no, more important, what do you think I should not know about you? That's maybe what I want to collect. Silence.
How many felons there were in the class, right?
How many what?
Felons? I don't know. So somebody should hide.
I do value my life, at least for a few hours. And you don't know the real reason why I left India and came here.
Exactly. You might be one. I don't know.
What do you mean might?
There you go.
Okay, so let's say I want to, I don't know, find something. Let's say average age, just for humor. Okay, I want to find the average age of a student in this class. Okay, each student is therefore a data point, or is an individual in this case. And what would be the variable of interest? Age. And age is what type of variable? Quantitative. Okay. So, you know that I have a variable called age. The value of that variable varies depending on which student I'm looking at. Okay. That would be what I want to do here. So, in this case, individuals would be each one of you, and we have right now 173 students. 2 students dropped out. I must not have done a good lecture in the first part because 173 turned out, but no. So, variable is age. That is quantitative. How the age is distributed is called a distribution. So, if I want to look at this, okay. So, if I have a variable called age, I'm not sure. This is interesting. It doesn't want me to write anything. Okay. So, let's say this is, what do you think is the youngest here? 19? 18? Oldest. Yeah, I'll just be kind with 25. Okay. So let's say there are this many 18, 19, 20. Okay, I'll just put values like that. Where the height indicates how many. When I list all the ages and list how many of each age they are, so I might have 15 people who are 18, 16 people who are 19, 45 people who are 21, so on, okay? When I list something like that, that is called a distribution. A listing of the values of a variable along with the frequency of occurrence is called a distribution. So every time you hear the word distribution, just think, it tells me how many people are at whatever value. So if I were to do height, you would get different heights on the x-axis. The y-axis would indicate how many people are that tall. Okay. So in this particular example, let's say this is 22, and let's say there are 75 of them. You would say, okay, the maximum, the value which has the maximum number of students is age 22 because there are 75 of them. Okay, that value is also called a specific term. The value that appears the most frequently is called mode. It's got a specific statistical term. Okay, so that's called mode. So let's take a look at this further. So we already seen this. Oh, categorical. So I'm not going to talk about this anymore. The question now is, how do we decide if something is categorical or quantitative? It's really very simple. More than number. One, if it's number and? That's right. You should be having a value, but that value, when you can manipulate that value. Just because I say 0 and 1 doesn't automatically make it quantitative. Okay? So if you have values and you can modify them or manipulate them and it makes sense, then it's quantitative. So it's actually very easy to decide whether it's quantitative or qualitative. So in this case, diagnosis would be qualitative or categorical, and age at death would be obviously quantitative. Okay. By the way, age at death, can you tell me the mode if there is any. Which value appears the most frequently? Which number appears the most frequently? They're all even. So all of them are the mode. Okay? Okay, so let's take a look at the ways we can plot categorical data. Very important. We are plotting categorical data. Okay? So, first categorical data is called a bar graph. In a bar graph, the categories are plotted on the x-axis, the frequency on the y-axis. Okay, the categories on the x-axis, the frequency on the y-axis. Everybody understand the term frequency? So if I were to ask you approximately what is the frequency of students wearing a hat in class, you would say how much? Approximately? 0? Nothing? You wouldn't say anything. What is the frequency of people wearing hats in class? Or, in other words, how many people wear a hat to class? 8. Fine. That's good enough. Okay. I don't know if it's true. How many people are wearing a hat in class? 1, 2, 3. I can't even see anymore. So the height would indicate the frequency. Now I want to ask you this. This particular bar graph on the marital status, it says never married, married, widowed, divorced. And on the y-axis, it gives you the count. So which group has the greatest frequency? Married. Okay. Let me ask you, think about this before you answer, okay? Is there a particular reason that the x-axis has to be ordered that way? Why is the x-axis ordered from never married to divorced? Is there a progression? I mean, did I have to put it that way?
No.
No, why? So what is the big deal there? How else could I have reordered it if I needed to? Ascending and descending of what? I could have done that. So is there a method to the madness? So if you want to develop a method to the madness, what kind of method would you use? If I ask you to create a bar graph, if I ask you to create the same bar graph without telling you never married is first and divorce is last, how would you have done it? Smallest to the great? And your logic for that would be, what would you be trying to illustrate? Before you're worried, sorry? Increase in frequency, okay, very good. What other method can you think of? There's no right answer, which should help you now. Any other way? Largest to the smallest, which is the other approach.
Alphabetical.
Alphabetical. That's not alphabetical. You could do alphabetical. That's fine. And then if you do alphabetical, what point would you be trying to get across?
Just trying to put an order.
Just put an order. Okay. So here is the trick. Anytime you create a bar graph, ask what is the objective. Okay. If you have a large number of groups and you want to do alphabetical, that's fine. If you want to illustrate a trend, maybe, or something that exists in a particular pattern, maybe you can order it differently. But really, bar graph, the x-axis can be ordered any way you want. Okay, there's nothing, rule of thumb that says x-axis has to be ordered the following way. This is true only for categorical because there is nothing here. Maybe in this case, can somebody think of why they did it this way?
Some sort of progression.
Some sort of progression, though I don't know what. I mean, obviously you can't be married without having never been married before. But the question then is, widowed and divorced, I guess you could have flipped either way, but okay. So now pie charts on the other hand approach the problem from a slightly different. So if you look at the count on married, it's about 110. You might ask, okay, what percentage of total people in this data study are married? If you ask that question, it's easier to look at a pie chart than to look at a bar chart. Would you agree? In fact, can you give me the answer straight away, approximately? What percentage of the people in that group are married? More than half. Okay. And that should come with instant recognition every time you have to share a pizza. Right? You know which part of the pie you want. Slightly greater than half. Okay. So pie charts have a different problem in the sense that they represent the proportion of the overall proportion. Now that pie chart is interesting because when you do Alex, you're going to get a pie chart exactly like that, which will tell you what proportion of the pie you have actually learned. And that proportion of the pie will become darker and darker. So the more you learn, the darker the pie becomes. So you know you're learning something, okay? And that's what the pie chart is. So here is a data. Can you identify for me the categorical variables and the quantitative variables before I? So quantitative would be?
The calculated percentages, the quantitative, the number.
So that would be counts. And the percent of top tens are percentages there, that's fine. And causes of death would be? No, causes of death would be what type of variable? Categorical. They would be a categorical variable. So if I want to do a bar chart, how would you order the values of the categorical variable causes of death? On the x-axis. Very good. Okay, so let's take a look at it. Here are the categorical variables, ordered in terms of, I think many of you suggested, in order of the frequency of occurrence. So looking at this bar chart, you immediately know the top cause for death is, see, it's a very clear graph. So if that is what they wanted to depict, very easy to pull that out. In fact, you can look at it and say, if you look at heart diseases, cancer, and cerebrovascular diseases, that pretty much accounts for, I would say, nearly 70-80% of all diseases in the top 10. Okay, but I can give you a more accurate estimate if I were to look at the same information as a pie chart. Very good. That's really what we're getting at. Okay, so here is your pie chart. In fact, if you ask 37, 67, 76% actually. So if you add up those three, okay. Now here is the beauty of it. The pie chart, you need to make sure that the total percentage always sums to 100%. Very, very important. Okay. Pie chart always 100%. That is something that you need to remember. Don't leave out categories because it will always do in relationship to what you select. So if you do that, that means you need to be careful that your labels match the percentages. The first pie chart on the top is the percent of deaths from the top 10 causes. Look at heart diseases. From the top 10, 37% of those diseases is heart diseases. But if you just look at the percent of deaths from all causes, heart diseases only account for 29%. Okay, the base is different. In the top one, you only have 10 colors, really, 10 pies, 10 slices. In the bottom one, you have a lot more. So make sure that your labels match the percentages. The first one is from the top 10, the last one is from all causes. Okay, make sense? Okay. So, can you look at this? This is a what kind of a chart? Bar chart. And what does it tell you? It gives you poverty before and after government intervention. And the yellow ones are before taxes and blue ones after taxes. Okay. That means after they intervened, the poverty levels are given in the blue bar. And the US is here. The last one. What can you tell me? It hasn't gone down as drastically as others. That's true. What else can you tell me?
Very high in the United States.
That is true. But it's also high in, for example, Ireland had 30% before government intervention. After government intervention, it had 12. What else can you say? Yes? Government intervention lowers poverty. That is true. What else can you say? You're missing one obvious conclusion. Yes?
I know someone already said it, but government intervention was not as effective as other.
Very good. Government intervention is not very effective in the US. Can you see that? It drops from 26% to 22%, while some cases, for example, France drops from 25 to 7%. So government intervention, yes, reduces poverty, but is not as effective in the US. Okay? My question to you now is, can I take this chart and convert it to a pie chart? Or you tell me. Can I do it in a single pie? No, the answer is no. Can I do it in two pies? And what would the two pies represent? You're getting me hungry here. Huh? Sorry? Before and after. Okay? And that would be what? So what would the pies represent? The first pie would represent before, but more specifically, what will each slice of the pie be? Countries, but what will the amount of the pie slice be?
Percent under 18
Sorry?
percent under.
Percentage. No, careful. Again, tell me again. Here's my pie. And here is US. What value should go in here? Will it be 26?
No.
Then, what number am I putting there?
Are you getting the difference?
I don't know, you tell me. I'm just doing what you guys are telling me to do. I know nothing.
The average relative to all the others?
How would I calculate that? What am I putting there? Yeah? So add up all the percentages? Where do I have raw data? I don't have raw data at all. But the yellow bar itself is a percentage. It's a percentage of people under poverty.
You can't do much of it.
Yeah, I think you can do one and pick the difference, like 4%, and this is what happened after government intervention.
But what will the pie chart represent then?
Percentage of a percentage.
Let me ask you this. If I do percentages, if each one is a percentage, right? If you add them up, what do you get? But does the percentage 26% in US the same as 26% in France?
No.
Totally, it's like dealing with euros and dollars. If you want to give me a €1 for $1, I have a currency trade for you. Okay? So you can't do that. You have to make sure that the units make sense. Just because you can add and subtract and convert it into a percentage doesn't mean you should do it. Okay? So think about what you're trying to do first before you go ahead and plug it in. So, okay. So we just went through an exercise where we looked at ways of plotting categorical data. Okay. We're going to now switch to quantitative data. And again, what is the key determining factor? Quantitative data allows us to manipulate them. Okay, that's really the key. But quantitative data has something that categorical data does not. Quantitative data, by default, has a natural ordering system. If I give you 3 and 5, you know automatically 3 is smaller than 5. Okay, so we have a natural ordering. So what that does is, it helps us plot the x-axis in a much more consistent fashion, because there's only one real way to plot x-axis. Okay, and so we're going to look at that. So there are two real big ways of plotting quantitative data. Having said that, the bulk of the time we will be spending on something called histograms. And most of these plots are a way of plotting a single variable at a time. We will soon talk about plotting multiple variables at the same time, but for the moment, in descriptive statistics, we'll describe only one variable at a time. Okay, we'll talk a little bit about stem plots and describing two variables at the same time. We'll come to that. And finally, when we stop at the end of quantitative data, we'll talk about time plots. Time plots is very interesting because time plots are a way of plotting observations over time. Can you think of something that you see pretty much every day which happens over time? Data, weather, stock prices, gas prices, fluctuations, all that is over time. Now here's the beauty of it. Anytime you have time plot, automatically x-axis is time. Don't even have to think about it. Okay, automatically x-axis is time. Okay, so we'll talk about that too. So here is information on the 50 states, and the values given are the percentage of Hispanic residents in each of the 50 states. Do you know that this year is the first time where the minority is actually the majority in the United States? If you lump up all the minorities, they are now the majority in the US in terms of demographics. Okay? So here is the percentage of Hispanic residents in each of the 50 states. Okay? And you know that that percentage is a quantitative variable and we want to plot it. Well, here is the first plot, histograms. Now, be careful with the axis. The x-axis is the percentage of Hispanics. Note very carefully. The x-axis is the percentage of Hispanics in a state. What is the y-axis? The number of states that have a value between 0 and 5. Okay, so in this particular case, there are approximately 27 states that have Hispanic percentage between 0 and 5% of their state population. There is one state, or maybe two, one state in this case, New Mexico, that has an Hispanic population between 40 and 45%. Okay, so we can actually go back to the previous slide, and New Mexico, why is it twice? Oh, that's rank order. Thank you. I'm wondering, I'm seeing more than 50. Maybe 2 glasses now.
Why is the percentage on this one different than the percentage on the qualitative?
Oh, on the bar charts? It is not different. Both are percentages, except they're totally different measures. For example, France population is different from the US population, right? So, if it's just percentage, if you're mapping it, that's fine. As a categorical variable, it comes into trouble when you add them up. Because when I say 26% in France, that can only mean maybe 5% in US. I mean, US has a population of 300 million. But here, the numbers, the percentage itself is the value that we are worrying about. We are not worrying about comparing New Mexico directly with Tennessee in one sense. We are just comparing the percentage itself. So, the question being asked is, what is the percentage of residents in your state? That's the question being asked. So if you ask that question, I can say that in New Mexico, the percentage of residents who are Hispanic is 42.1, while in Utah, it's only 0.9%. So if you look at the next graph, this says, the x-axis says, identify all the states that have percentage of residents between 0 and 5% Hispanic. How many states are like that? So we have removed the problem of disparate numbers out completely. So the x-axis is where the change is. If the x-axis had been states and we try to convert it to a pie graph, we run into the same problem. Okay? Because it's a numerical value, I don't care. So if I took the world poverty graph and I said identify how many countries have poverty between 0 and 10%, I could have done exactly the same. Okay, so the x-axis again is the percentage of Hispanics. The y-axis here indicates how many states have that value. Very important difference, okay? So notice that I didn't have to worry about x-axis values because it goes from the smallest to the largest automatically. Natural ordering. Okay. The only question you might ask is, can you think of one question you should ask? Yeah.
What state falls under the percentage?
That we know all the states. Basically, if you add them up, if you add all the height, it'll amount to 50. But there's one more question on the x-axis you should ask. Don't assume anything. Why did I have to make up the x-axis the way I did? Is 5 a magic number? Did I have to do 0 to 5%? Why couldn't I have done 0 to 4%? Or 0 to 10%? There is no magic value. So the values, the grouping that I choose on the x-axis itself is a rule of thumb. Remember, if I choose 0 to 50, what would happen to the graph? It will expand, and what will be the height of the graph? Wouldn't you get a totally different picture than what's depicted here? So, if I choose appropriate values, if instead of 0 to 5, if I choose 0 to 7, you'll get a totally different picture. So the question you should ask is, how do I choose those values? Well, there are rules of thumb. But fortunately for us, these rules of thumb have evolved to a large extent. And since most times histograms are plotted by software, we're going to let software predict that. Okay? But you have to remember, that is your assumption. There is nothing that says it has to be 0 to 5 here. Okay? That's a very key assumption. Okay? So we have seen that. Okay? Now, we're going to take a look at another approach which we can do by hand, and it's called a stemplot. Okay, so let's do a stemplot. Stemplot basically divides the values into a stem and a leaf. Okay, in this case. So let's just, for argument's sake, I can take the data of 50 states, but we can just come up with some quick example. So let's say I want to take a sample of 10 students. Okay. And I want to create a stem plot of how much money you have left, which is probably 0. Yeah, let's say how much money you have left after spending on all these books and things like that. Okay. So I'll ask for a random, technically it's not a random sample, I'll ask for a volunteer sample of 10 students. So I won't even look at you, just give me some numbers, I'll put it down.
100.
You have $100 left?
30.
60.
0. 400.
I know a nice restaurant after class. I don't know how that works, I'll put 0. What else? Okay, so we got 1, 2, 3, 6, 9, one more.
75.
Okay. So this is the amounts I've got. Okay, so I want to create a stem and leaf of this. So the first thing I need to do is order them from smallest to largest, but I'm small data set, so I can actually do that visually. So I have to divide them into a stem and a leaf. So here's the very simple. What the last value is always the leaf, okay? So this is how it works. So the first number is 0, which we had. So here is my stem. My leaf, I have how many zeros? Here's 1, here's 2. So 0, 0, okay? Then the next value I had was 20. So basically, I don't have any ones, so I'll put 2, 20, then 30, then what else I had? 50, 60, 75, 100, 400. I'm missing one. 4. So 4 is nothing but 0, 4. That's how I would create a stem and leaf. Okay. So basically the leaf is the last part and the stem is everything else. If I had a large number of numbers for this, that will tell you how the data looks. It gives you a pattern. Okay. So I might have a pattern for the example that we just did. So I'll take a look at that. But that's your stem and leaf. Now, when we didn't have computers, this was a great way of looking at it, but you can see that if I had 1,000 numbers, what would happen? So basically, I'll kill myself doing stem and leaf, right? So, you're really not very efficient for doing such large data sets. It's great for small data sets, so we'll just worry about that. So here is the stem and leaf, I guess. Here's your stem and leaf for the values of this. Okay, so it's ordered and you can see the stem and leaf that's put down for that. Now looking at that, you can see very clearly the pattern. What does it tell you? What does it tell you? The bulk of the states have percentage of Hispanics, maybe 9% or less. Right? That's where the bulk is. Everything else is sort of, there are few states with really large amount. In fact, they haven't completed the problem because New Mexico doesn't even come. New Mexico would be here somewhere, 42-1, somewhere here. Okay? So, yes?
I don't understand the purpose of this.
Oh, so isn't that more graphically descriptive than looking at 50 numbers? So look at the shape.
Okay.
So it just says that the bulk of the people are on the top, which is lower percentages.
Oh.
So it's a graphical way of looking at the distribution of data. Okay, but histogram is a lot more colorful and a lot more informative, and that's what we're going to really land up doing more and more. Okay, but stem and leaf, that's what it does. So we have done this. You can do the same thing with what is called as a back-to-back stem. I'll leave that for you as an exercise because all you're doing is using the same stem and creating a leaf on one side here and a leaf on the other side here. Same thing. Okay, so really not going to do that. Okay, so we talked about this. Histograms. And the problem with histograms is that we need to define the area or the width of the histogram. Okay, in this case we defined it as 5. It can be 2, it can be 10. The question is when. What we are looking for is a histogram that allows us to create some kind of a smoothed curve on it. Why? That gives you some kind of a regular distribution value. That's really what we are going to look at. But you can define a histogram in at least 3 ways. One is the shape, and many of you are probably aware of this shape. Have you seen that before? What's it called? The bell curve. Okay, that's what we're going to study a lot. In fact, the end of this chapter studies that curve, which is called the normal distribution. That's the shape. But that's not the only shape you can have. You can have a shape which looks like that. That particular distribution is called exponential. And where does that shape apply? In fact, this shape tells us the frequency or the probability of accidents in airline crashes. Interesting. It also tells you if you are, let's say you're a manager of a Taco Bell and you want to know how frequently customers are going to come, this is what will tell you. That tells you the time between customer arrivals. So different shapes, different things. In fact, there's a shape which looks like this. It's called the triangular distribution. That tells you, for example, how long a light bulb will stay on. So different shapes give you different characteristics. Okay? Center. Center means, on average, where does the curve belong? In this case, this is pretty even, so you can say the center is somewhere here. This one, maybe the center is somewhere here. In this one, the center is obviously this part. So the center is where you are. Okay, so if I am data, how I look is my shape, where I stand in the room is my center. The final characteristic is spread. How much of the room I occupy is spread. Having said this, spread is the most important problem we have in statistics. Spread is nothing but variability. The more variability we have, the greater the problem we have getting results from it. If all of you were identical, I could give you an excellent lecture. But because you each have a different learning style, therefore there is more variability, we have problems. Similarly, in statistics, in fact, dealing with data, the greater the variability, the greater the problem. Really. So every time you think about this, worry about variability first. That's your key. If you can handle variability, everything else is taken care. Okay. For example, if you are in a, I actually went to grad school in Minnesota, and I used to love the cold weather. In fact, I still do. You might probably thinking, I actually come originally from a country where the low temperature would be 95. Okay. From there, yeah. I mean, I live right on the Bay of Bengal, which is about 5 minutes, not in 5 minutes, about 200 yards from the bay, literally on the beach. And I used to look at this and say, what are these people doing in the beach? I mean, in the middle of the afternoon, I could never understand. Of course, they were trying to get my suntan, but they never could. So, but my point is that I come from a country which is really hot, and I went to Minnesota, and I used to love the winter. Why? The moment it snows in, say, November, you could walk out with your cross-country skis and never worry, because for the next 4 months, you know that snow is going to be on the ground. I used to love it because I knew exactly every day it's going to be cold and snowy. I knew that. I come to Kent, I go, oh, look, snow. I go grab my cross-country skis. By the time I walk out, it's already melted. Variability creates problem. If I knew it's going to be cold, I'm ready for it. I never know now whether it's going to snow, slush. I don't know what the weather is. In fact, I still haven't gotten out my fall jacket. I'm still on my summer clothes. Hence my short sleeves. Okay? That's the weather. So variability is where the problem is. It's not, once you know something is consistent, it's easy to deal with. It's easy to come up with a solution. When you have variability, you have problems. Okay? So here are some common distributions here. This distribution is called symmetric. Why? Where do you think the center of this distribution is? Right in the middle, correct? That's your center. Would you agree that if I look at that center, the left half and the right half balance each other approximately? Therefore, it's symmetric. Approximately. Not be exact, but equivalent. Okay? That's symmetric distribution. This is an example of a skewed distribution. In fact, this is an example of a right skewed distribution. Why is it skewed? That means the center is no longer in the middle, but the center is going to be somewhere here. It's skewed to the right. Similarly, so if I were to draw a distribution, this is an example of a right skewed. It'll look like that. An example of a left skewed, well, I guess this is not a left skewed, but a left skewed would look like that. Okay? This is example of a more complex distribution because it's really two. There's one distribution here, one distribution here. Okay. This distribution here is more right skewed. This distribution here is actually more symmetric. Even though it's got two pipes, it's actually more symmetrical. Okay. If you look at it right in the middle, it's sort of balanced. It doesn't have to look nice. It just has to look balanced. Okay, so we'll worry about it. Most times we are going to be dealing with this distribution. Outliers. Okay, so whenever we look at distribution, again, many of the terminology that I'm giving you today, we are actually going to look in a lot more details as we start putting numbers to these things, okay? But what I want you to do is whenever you look at this distribution, ask yourself, what is it giving me? When you look at something symmetrical, you know it's very well balanced. You know if you take somebody who's average, then approximately half the people have better scores and half the people have worse scores. If you take a look at distribution that is skewed, you know that analysis is not correct. Similarly, when you look at distributions, you can look at things which are called outliers. Outliers are values that look very different from the rest of the data. Now, are they incorrect values? No, not necessarily. Do you know of things that are outliers? New Mexico would be an outlier with 42.1%. If I were to plot, for example, household income, do you think I would identify outliers? Right? You would identify outliers. Why? Because you know now, actually, this is a very interesting thing which I didn't realize. About 16% of companies in the world own more than 50% of the wealth. Just 16%. This is the whole world. Okay. But in the US, we now know that 1%, right, which is actually not exactly correct because there's a 0.1% who own more than close to 20% of the national wealth. Okay. So we're talking a really, really small percentage who have a really, really big share of the national wealth. That would be an outlier because that value doesn't fit the rest of the data. Doesn't mean it's incorrect. It just means it's very different. And many times, it's important for us to identify outliers. For example, if you're digging for oil, you're looking at a geological formation which is not like the rest of the formation. You're looking for an outlier. Okay? So, outliers are very important. You need to identify that. So, in this particular case, this would be an outlier and this would be an outlier right here. Okay? Well, Florida makes sense, right? Percentage of state residents age 65 and over. And that says between 18 and 19%. Actually, that is underestimating it. Florida right now, it's around 23, 24%. Okay. In fact, there are counties in Florida where the average age is about 69. Okay, so rules of thumb, we're not going to worry too much about it, but you can try different rules to do histograms. So we'll worry about that. So let's take a look at time plots. One thing about time plots, you always know that the x-axis is time. There is no question of even worrying about it. Okay. So what we are looking for, are there patterns in time? That's really what we are looking at. So here are some examples. So this is a pattern and you notice a trend. Even though there is great variability, the ups and downs, you know that the overall price is going up. In fact, if you were to plot gas prices, this is how the trend would look. In fact, if you were to, how many of you use something like Gas Buddy? Okay, if you need to fill up gas, please do it today because prices are going up in the next 2 days and the probability of that is 85%. Okay, so if you need to fill up gas, now today would be a good time to do it. Okay, so that's a trend. Trends are overall directions. You know gas prices, prices of oranges, prices of oil, they all have an increasing trend. Okay, even though you have great fluctuations from day to day. So while you plot it over time, if I were to plot, for example, the average value here versus the average value here, you can see that one is higher than the other. Okay, so we can have trends, which tells you the direction. We can also have fluctuations that happen seasonally. For example, snow shovels, right? I mean, or snow blowers. You buy them in winter, in summer you buy lawn mowers, right? So there are seasonal fluctuations that happen also. So this is what your seasonal variation. I don't know where they got it. It looks like a slinky. That's fine. Retail prices of oranges. So is there a trend in this? Do you see a trend in prices of oranges? Or are they telling you that you'll experience a high once you drink orange? No. It goes up a little bit, I think. So, how about something way, way, way before you were born? 1918. The influenza epidemic. Okay, so here is a time plot from week 1 to week 17, which tells you the number of cases diagnosed and the number of deaths. Tell me if you see anything. The one in blue is the number of cases, the one in red is number of deaths. Tell me what you see. The x-axis is the week, the y-axis on one side is the number of cases, and the other side is the number of deaths. What can you tell me?
As the number of cases per diagnosed, the number of deaths increased.
Okay. What else can you tell? I mean, does it happen in the same week? What?
About a week difference.
There's a week difference, right? You can see the lag? Can you see the lag in terms of patterns between those two? See, that's a very informative thing that you can get from plotting two different things on the same chart. Obviously there's a lag between diagnosis and eventual, in this case, death, right? As the number of cases goes up, the number of deaths also go up, but there's a lag between those two. So you can see that the time plot is very informative, especially when we are plotting something that's related. And notice another thing, the y-axis are different. On the left-hand side, they are in thousands. On the other side, the second y-axis, they are in hundreds. That's okay. Fortunately for us, software will allow us to do this very effectively. Okay, that's the advantage of using software. So this is part 2 of what we did last time. Remember, what we are trying to do is to describe data. And we did it graphically last time. But before we did that, we divided data into variables into two parts. Quantitative variables and qualitative or categorical variables. Variables that are quantitative are variables that can be manipulated. The numbers can be manipulated. We can add them, subtract them, divide them, so on. Those are quantitative variables. Age is a quantitative variable. Temperature is a quantitative variable. A qualitative variable or a categorical variable puts values into groups. So gender would be a qualitative variable. Whether you pass or fail would be a qualitative variable. Even though I can define pass and fail as 1 and 2, those numbers cannot be manipulated. I mean, you can't say 1.5. What is it? Neither pass nor fail? It doesn't make sense. So qualitative variables are variables that divide data into groups. Quantitative variables are data that are described by numbers that can be manipulated in some sense. Okay. Now, last time we saw different ways of describing or displaying these variables. If we are dealing with categorical variables, we use bar charts and pie graphs. If you're using quantitative variables, we use histograms and stemplots. Okay, so today we're going to take the same thing, but actually describe the data using some summary measures. And many of the summary measures should be familiar to you. So the first thing we're going to do is talk about measures of center, and the mean or the average and the median are two measures of center. Then we're going to talk about measures of spread, and one of them is the standard deviation. And last time I talked about both center and spread. Which one did I tell you is more important for us? Spread. The biggest problem in dealing with the numbers or with data is always spread. Okay. If you have a data set with very low spread, low variability, it's very easy to deal with it. Anytime we have a data set with high variability, lot of problems. So in all these things, when we look at it, the problem is always to see what the spread is. That's where we have to figure out. Okay. So what is spread? What is mesh center? So if you define the room as data, and if I am the location, where I'm standing would be the center. How much of the room I occupy is the spread. Okay, so if the mean is here, this is where it is. If I move there, then the mean is there. Okay, that's the center of the data. How much I occupy is the spread. The more you occupy, that means more things you need to know before you can tell me what's happened. Okay, so remember that high spread is bad. We need to do more things than to come up with the right answer. So remember that always. Okay, so let's start with the mean. The mean is very simple. The mean is nothing but add up all the numbers and divide by the number of items. So if you look at it another way, the mean is nothing but a total or a sum of all the values. So in this case, the sum of the heights is this, and we have 25 people, so the average is 63.9. The question is not how we calculate it. It's actually very easy to calculate. What does it tell you? So what do you know now about that 63.9? Once you know the average, what does it tell you? Most women are 63.9. Is that true? Do you see anybody there 63.9? One person. There's only one person in that whole data set with 63.9.
The average 63.9 inches.
That we know. What does that tell you? Yes.
Most women are around that height.
Is that true? When you say around that height, what are we talking about? Well, in this case, 58.2 to 69.6. So, okay, let me rephrase this. Let's see if I can give you a much more stark example. What is the average income for a household in the United States?
Around 55,000.
Okay, 55,000. What does that tell you about the households in the U.S.? That's true. What else can you tell? Can I say that 50% of the households earn less than 55,000 and 50% earn more than 55,000? No? Why can't I say that? What do you know about the income distribution in the US? It's wide, but what else do you know?
Unequal.
Sorry?
It's unequal.
Inequality is there, but what else do you know?
Outliers.
Define outliers.
There's like a very small amount of people that make a lot of money.
Okay, so there's a small percentage of households earn a large amount of money. What does that do to the mean? It increases it. Okay, so let's take a simple example. 1, 2, 3. What's the average? 2. 1, 2, 101. What's the average? How much? Okay. Is it 34? What is the average? Let's see if you guys can add up three numbers and divide by 3. Close. That's good though. Okay. What happened? One number. Look what happened to the mean. It got pulled towards that one number, didn't it? So what does that tell you? The mean is influenced by extreme values. So the mean is 55,000. Can you now tell me something about the distribution of household income? Let me rephrase the question. What percentage of households have an income greater than 55%? Okay, let me rephrase that question again. Is it equal to 50%, less than 50%, or greater than 50%? How many say less than? Okay, how many say greater than? How many say equal to? Okay, there's still about 30% not saying anything. The answer is less than. Why? Because the 55%, $55,000 is being influenced by the small group that's earning several $1 million. Therefore, the bulk, the majority of households, therefore, earn less than 55,000. So here is one big problem with the mean. The mean is influenced by extreme values. Therefore, we use the mean as a good description only when we have somewhat symmetrical data. Okay, so let's take a, so here is a distribution. Is this a histogram or a bar chart? It's a histogram. Why? What kind of data are we dealing with? Numerical data, quantitative data. Therefore, this is a histogram. Does that look pretty symmetrical? The distribution? Right? Therefore, the mean is a good indicator of the distribution. It's a good measure of central tendencies. Okay? Now, let me show you another example. Take a look at this. Is that a symmetrical distribution? Same mean, approximately. But don't you think the one on the bottom looks a little skewed? In fact, if you were to look carefully, and I'm going to show you that in the next page, you will see that the bottom distribution is actually composed of 3 different types of data. Therefore, that average 69.6 height of all plants is really not a good indicator. So whenever you're using the mean, you always have to be careful. What is the data? First, plot it. If the plot looks symmetrical, if it's all uniform in one sense, dealing with the same type of data, great. The mean is a good indicator of what the distribution is telling. But if it's something like the last one, and here is what it looks like actually, so we actually have 3 different values. Okay, you can see that the blue one is quite symmetrical, therefore the mean 63.9 is a good indicator of that. Okay, but in the pink one, it's sort of skewed to the right. Similarly, the red one is skewed to the right. Therefore, the mean on those 2 cases are not good indicators of those values. Okay, and we're going to see that. So let's see. So we now know that the mean is influenced by extreme values. Let's take a look at another measure called the median. Okay, what is the median? The median is the midpoint of the distribution. So regardless of what data you give me, the median is always the middle value when you arrange the numbers in either increasing or decreasing order. That means if I tell you that your score is the median score, you know that 50% of the students got a score less than yours, and 50% of the students got scores greater than yours. Having given you this description, and knowing what we said about the average household income, can you tell me if the median income will be less than 55,000, equal to 55,000, or greater than 55,000? It will be less than 55,000. Very good. Why? Because we knew that the mean was influenced by values, high value. Therefore, it got pulled to the right. Okay. So we know that when I look at the mean, more than 50% were below the mean. Therefore, the median has to be smaller than the mean. Anytime the mean is greater than the median, we say that the distribution is right skewed. The mean is to the right of the median. The median is the central point always. Okay. So let's take a look at the median. First, sort the observations, smallest to the largest. It doesn't matter if largest to smallest or smallest to the largest. We'll start with smallest to the largest, okay? If the number of items is odd, the median is n plus 1 by 2, basically the middle value. So in this case, we had 25 points. So the median is the 13th point. And the 13th point in this particular case is 3.4. So the median value is 3.4. That tells you that 50% of the items will be smaller than the median and 50% greater than the median. So 12 items on each side. Okay, that's how the median is. What if n is even? Well, if n is even, then the median value is the average of the middle 2 values. Okay, so if you have 24 data points, the middle 2 values are 12 and 13, therefore the mean of 3.3 and 3.4, which is 3.35, is the median value. So if you look at the number 3.35, you see that you have 12 items below the median and 12 items above the median. So let's take the previous example we did for the mean and show you something very simple. 1, 2, and 3. What's the median? How many items do we have? Odd or even? Okay, so what's the median? 2. Very good. 1, 2, 101. What's the median? What does that tell you about the median? The median, other than the wisecrack, no, 2. The median is not influenced by extreme values. Okay, that's the beauty of the median. So when you have a distribution which is not symmetrical, the median will be different from the mean. And the median is more representative of the household income. So in our case, the median income is probably around 40,000. That tells you 50% of the households earn less than $40,000 a year and 50% of the households earn more than $40,000. Okay, that's the difference between a mean and a median. If the distribution is symmetrical, what can you tell me about the mean and the median? They will be very close. Very good. What if the distribution is left skewed? That means we have some very, very small numbers. What will be the relationship between the mean and the median?
Median will be greater.
The median will be greater, or the mean will be to the left of the median. It's called a left skewed distribution. Okay, so you can see what I just told you. So a symmetrical distribution, the mean and median values will be similar. In a left skewed, the mean is to the left of the median. In a right skewed, the mean is to the right of the median. This is an example of our income. And I don't know what the left skewed. Can you think of something which is extreme to the left? Other than my wallet? I'll come up with some examples. Okay, so let's plot this. Okay, so here is an example, and do you see something which looks very different from the rest? Well, you should. I've highlighted that for you, and if you still can't see it, I'll put some arrows. Okay. Looks very different from the rest. What will the effect of that value have on the mean? It will skew it to the right, correct? So outliers influence, so because of this, the mean might shift somewhere here. Without that, where do you think the mean is? Or approximately between 3 and 4, right? So approximately 3.5. So the average doesn't like the mean. So disease X sounds very mysterious. On average, 3.4% of people dying over time. I hope it's not this class where X stands for stats. So, but okay. So with outliers, look at what happened to the mean, got shifted to the right. So here is your first thing you need to watch out. Anytime you're dealing with raw data, look to see if there are outliers. Outliers are values which are very different from the rest of the data. If you have values which are very different from the rest of the data, it's going to influence the mean. Do you think it'll have much effect on the median? Probably not. Okay, that should give you an indication. So if I were to draw the median with the outlier on, where do you think it will be? 4 or closer to 3.4 in one. Yeah, that's fine. As long as you gave me the right direction. Okay. So now tell me, which is symmetrical, which is skewed? There are only two choices. Top one, symmetrical. Therefore, what can you say about the mean and median? They are approximately the same. On the right, on the graph below, what kind of a skewness is it? Right skewed. So what is the relationship between the mean and the median? Means to the right of the median. Everybody make sense? Okay. Good. See, classes like this I can deal with. So let's talk about quartiles. Anybody know what a quartile is? Okay, let me rephrase this. If you want to look at your exam score, what percentiles would you want your score to be? Do you like a high percentile or do you like a low percentile? Yes.
You want to be in the upper quartile.
You want to be in the upper quartile. What does that mean?
It's the upper 25% of the.
Okay, so upper 25, let's say 89. Is our 89 in the upper quartile? Okay. So 89th percentile means what about your score?
You are in the upper quartile and you've done well.
Well, what else can you say about your score? If you're in the 89th percentile,
Scores 89%. Like you were the top 89%. We scored higher than 89%.
very good. Okay, so I'll rephrase it. 89% of the people had a score less than yours. Okay? So, by that definition, what percentile is the median? 50. Very good. Median is nothing but the 50th percentile. Okay? Quartiles are nothing but multiples of 25. That's it. So it's going to be very easy to figure out the 25th percentile. How do I do that? First, identify the median. Next, look at the values below the median. We have 12 of them. If you have even number of items, what is the median value? The average of the middle two. The average of the middle two is right here. That is the 25th percentile. How do we identify the 75th percentile? Very simple. Take all the values above the median and find the average of the middle two, because we again have even number of items. And therefore that's the third quartile. So a quartile is nothing but doing the median calculations on two different data sets. You first take the whole data set, split it into half, take the top half of the data set, calculate the median for that half, that gives you the 25th percentile. Take the bottom half, calculate the 25th or median again, that gives you the 75th percentile. That's it. Very simple calculations, okay? If you know how to calculate the median, you know how to calculate the first and third quartile. Now, I can ask you 10th percentile, 20th percentile, so on, but we don't have to. Many times we will just use statistical software to calculate percentiles for large data sets. But the interpretation stands. Okay, because these are the quartile values, the interpretation for quartiles is similar to the interpretation for the median. 25th percentile means 25% of the values are less than the quartile, 75% greater than the first quartile. That's it. Same kind of interpretation as we do for the median. Okay. Having done this, we can now put a graphical representation for all this. It's called a box and whisker plot. Okay. So here is a 5-number summary. So here is the data set on the left-hand side, and here is a box plot. The box itself, let's concentrate on the box first. The lower edge of the box is the 25th percentile. The upper edge of the box is 75th percentile. And the line in the box is the median. Okay. So in this particular example, the median is approximately 3.4. That tells you 50% of the data are below the median and 50% above. Now, normally, this point here is the minimum value in the data set, and this point here is the maximum value. Sometimes you will get a point which will be above the whisker, it will be something like a star. Those are normally outliers or values which are very different from the rest of the data set. Okay, I'll show you an example of that. But here is the interesting thing about the box plot. Just by looking at the box plot, many times you can figure out whether the distribution is symmetrical, whether it's right skewed or left skewed. But what the box plot doesn't tell me is the value of the mean. Can you look at the box plot and tell me what the average is? In this example, you should probably be able to tell me.
Well, it's symmetrical.
Very good. It's symmetrical, so the average is approximately 3.4. Doesn't the box plot look really symmetrical? The line in the middle and the box plot evenly spaced and the whiskers evenly spaced. Okay, but normally we can't tell that. Okay, so let's take a look at that. So, can you tell me what kind of a box? There are two graphs here and two box plots. Tell me which goes with which. It should be very obvious. This is a symmetrical plot, and that goes with this. This is right skewed. Right skewed means what? We have some very small, very few large numbers. Okay? And that's why you have a long tail. Okay. Now, in this box plot, if I were to draw the mean, where would I draw it? Where would I put the mean value if I were to put a mean onto that box plot? Higher than? Really? You want me to put it somewhere here? Well, at least the direction is right. I don't know what the values are. So you're fine. Okay. I'll take it. Suspected outliers. It's like saying bad criminal? No. Outliers. Okay. Outliers are troublesome data points, but many times we actually look for outliers. Okay. When do we look for outliers? Whenever we are, I gave you an example of oil survey. Anytime they do a geological survey, they are looking for outliers in your data points, because those data points indicate soil which is very different from the rest of the data. Okay, but we need to be able to watch out for them and to be able to change our statistics appropriately. So one way to do that is through this interquartile range. What is interquartile range? Let me go back to our box plot. Interquartile range is basically this distance from this edge to this edge. The difference between the third quartile and the first quartile. In this case, Q3 minus Q1, which is 4.35 minus 2.2, which is 2.15. That's your interquartile range. So we are going to use a rule of thumb to identify outliers using box plots. And the rule of thumb is start with the interquartile range. And in the previous example, it was 2.15. Multiply that by 1.5. That's your rule of thumb. What does a rule of thumb mean? Anybody know another word for that? Heuristic. It's just something that we figured holds true many times, therefore we'll just use it. There's no proof that it actually works all the time. There's just data that supports it. Okay, so we multiply that by 1.5. So here is our example, and when you multiply that 2.15 by 1.5, we are going to get something smaller than that. We get 3.225. So you take the 2.15 and multiply that by 1.5, you get 3.225. Here is a data point. This data point is a distance 3.55, which is greater than the amount that we calculated. When a point is greater than 1.5 times the interquartile range, we say that that point is a probable outlier. It's again just a rule of thumb. For you, fortunately, if you were to take this data set and put it into JUMP, it will automatically show you that. Okay, so I don't want you to worry too much about it, other than to know that it's a rule of thumb that we use. Okay, so this is the second and really most important measure of data that we are going to study, called standard deviation. It's a measure of spread. And we know that higher values, we have greater problems. So how do we measure spread? There are different ways of measuring spread. What standard deviation does is, it looks at how far data are from their mean. So in this particular example, we have the mean at this point, and the blue ones are all the data points. It measures how far they are. So you might say, oh, that's great. Let me just add up all the differences. Okay. So what do you think? Suppose I take the value minus the mean. All these values are positive values. Agreed? Okay. If I take the value, this is below the mean, therefore all these values are negative values. If I add them up, what do you think will happen? They will all equal 0. That's the property of the mean. Okay. So the mean by default lies in a place so that when you take differences from the mean and add them up, it will always add up to 0 by definition. So we say, that's interesting, but I don't really care whether the difference is positive or negative. What I really care is how spread out are the data. So what I'm going to do is very simple. I'm going to take each of these differences and square them. Okay. If I square them, positive values remain positive. What do you think happens to negative values? They become positive. Therefore, what I get is a measure of squared differences from the mean. So here is the very simple strategy. I'm going to explain it in words, then I'll show you the formula for calculation. Take each value. Okay, back up. Calculate the sample mean first. Take each value, subtract the mean from it. Square that difference. Do that for all the values. Add up all the squared values and divide that by the number of items minus 1. Okay. But the basic rule is you are adding up all the squared differences of values from the mean. So before we even do any calculation, let's see if you can do this. I just give you 3 numbers. What's the mean? 2. Okay. So let's calculate the spread. I'm going to take each number, 1, subtract the mean from it, and square it. So this is how much? 1, 0, and this is 1. Agreed? So this is equal to 2. That is the sum of squared differences of values from the mean. Now, to calculate standard deviation, we have to go one more step. Why? Would you agree that if instead of 3 numbers, if I had 5 numbers, you will automatically get a bigger value most likely than 2? Because the more things you add, the more likely it's going to be bigger. So how do I know one set of data has a larger standard deviation than the other? The way we do that is to account for the number of items we have. So this particular data set, I'm going to take the value I got and divide it by the number of items, which is 3. I have 3 values. I'm going to do this minus 1, and I'll talk about that later on. But for the moment, just presume it's always n minus 1. If I had it 5 items, I would do 5 minus 1 in the denominator. So this turns out to be 2 divided by 2, or 1. This is called variance. And standard deviation is nothing but the square root of that number. In this case, 1 again. Okay? So both values are the same. But that's it. That is the measure of spread. So if I ask you the following question now, okay? So in this case, 0, 2, and 4. What's the mean? 2. Now notice, this data set had 2. This data set had 2. Which one do you think will have a higher standard deviation? Why? Because the values are further away from the mean. Do you see it? Does that make intuitive sense? The second data set, even though it has the same mean as the first, aren't the values spread out more? They are further away from the mean. 0 is 2 digits away from the mean compared to 1. 4 is 2 digits away from 2 compared to 3. Spread out further. Therefore, the bottom one is going to have a higher spread. Okay, that's it. The calculations are very straightforward. Yes?
What's the underlying word?
Variance. Sorry. My handwriting is horrible, to say the least. Okay, so I don't know what else I have on this page. Oh, like this, so you can actually see what's written there. Actually, I just wanted to show off my fancy eraser on this. So the way we calculate the variance is you take each value right here, subtract the mean from it, square the difference, and this is nothing but the summation sign, or add up all of them. Okay? And when you add up all of them, you divide by n minus 1, where n is the number of items. So if you want to understand the formula, if you understood what we just did, that's basically the formula. Okay, so there's no real big difference in calculating the variance. Once you calculate that, you take the square root to get the standard deviation. Now you got to be careful. Let me ask you this. If I give you in 4 and I ask you to take the square root, what would be the answer? Plus or minus 2. Agreed? Square root is plus or minus the value. So the question is, should I take plus 2 as the answer or minus 2 as the answer? Well, spread is a measure of distance. So we only take positive values. So standard deviation is the positive square root of the variance. Okay, so standard deviation is the positive square root of the variance. So what are the properties of the standard deviation? To calculate the standard deviation, we need the mean. So how many data points do we need at a minimum before we can calculate the standard deviation? Or let me rephrase this. If I have only one data point, can I calculate standard deviation? No. So you need at least 2 data points. When will the standard deviation be 0? When all the points are the same. When all the points are the same, the average is equal to each of the points. Therefore, the difference is 0. So if your numerator is 0, then the standard deviation is automatically 0. Okay. So think about this. The further away the points are from the mean, the larger the standard deviation. Closer the points are to the mean, the smaller the standard deviation. Okay. So we're going to look at it visually, and when we look at visually, it makes a lot more sense. Okay. So standard deviation is not resistant to outliers. That means outliers will influence the standard deviation. Outliers influence the mean, and therefore it influences the standard deviation. So remember that. Here is the interesting thing. Standard deviation has the same units of measurement as the original observation. What does that mean for us? If the data you are given is in, say, pounds, when we calculate the standard deviation, it is in pounds. But if we calculate the variance, it is in pounds squared. Square of the original units. That's why we go back to standard deviation, because the answer is in the same units as the original data. What does that tell you? If standard deviation has a unit associated with it, if I calculate the standard deviation of household income in the US and the standard deviation of household income in Europe, can I compare them directly? Okay, Europe has what currency? At least the bulk of. Okay, the bulk of Europe, which is euro, for whatever it's worth now. In fact, it's a good time to go to Europe. It's never been as close to the dollar as it's been now. So Europe has euro. So the standard deviation there will be in euros. The standard deviation here is in US dollars. 2 different units. So if you need to compare something, we have to convert both of them to similar units. We can't compare them directly. Okay, so standard deviation has units. So remember that part of it. Okay, so we already talked about this. Because the standard deviation is not resistant to outliers, standard deviation makes sense when we are dealing with symmetrical distributions. When we have outliers, we need to worry about them. Okay, so we'll take care of that. So when we come to it. So So can you see, tell me what you think about these two statements. First one says, Middletown is considering imposing an income tax. City Hall wants a numerical summary of a citizen's income to estimate the total tax base. Should we use the mean or the median? Why? Sorry? What's the key word that tells you to use the mean? Income by definition doesn't tell you to use the mean. No. Are you just going through word by word? Total. If you have the average and you know there are 10 people, can't you figure out the total? How much money you have? I'm sure Friday is coming up. You guys probably be drinking somewhere. If you need to get the total amount, you take the average, multiply by the number of people, you get the total. So total tax base, mean is probably a better idea. What about the second one? They want a numerical summary of family income. Which is a better measure? Median. Why? Median incomes gives the point where 50% below and 50% above, it is resistant to outliers. Okay, so that's what that is.
How do we answer questions?
Answer questions, either 1, 2, or 3. 41. Everything gets moved by 3,000. Is that what happened? Okay, what distribution is that anyway? What's the answer distribution? Symmetrical, left skewed, right skewed? That's called the standard normal table, and that's something we will use a lot. And it's available on your website under the downloads folder. So you might have to share because I won't have enough for everybody. So when we were talking about describing data, especially quantitative data, we were describing it using histograms. Okay? We also talked about distributions that were symmetrical and skewed. Well, what you're going to see today in this particular part of the chapter is a distribution that is perfectly symmetrical. And it's going to have a specific name which you know as the bell curve. Okay? When we describe data using a mathematical model of the data, we're really describing what is called as a density curve. Okay? Here is the things about density curve. The total area under the curve is always equal to 1. Okay, the total area under the curve is always equal to 1. Why? Because now I can start very simply and say, if the total area is under than 1, and if this is symmetrical, by the way, that's a straight line. Okay, and that's even before I started drinking. Okay. 50% of the values are less than that and 50% greater than that. So if somebody says, let's say this number is say 7, somebody says, what is the probability that my vocabulary score is less than 7? I can automatically say, oh, 50% of the curve is less than 7, therefore the probability is 0.5. Or somebody says, what is the probability I'll have a value 10 or less? I can say, the probability I'll get a score of 10 or less is the area under the curve. If that area turns out to be 90%, then my answer is 0.9. So the total area under the curve is always equal to 1. The probability of a value appearing is the probability of that value and whatever area, either the value less than or greater than, doesn't matter. Okay? So this is called a density curve. And we're going to deal with a specific density curve called the normal distribution. So the table I give you gives you the probabilities for values under that density curve. Okay? See, here are different types of density curves, and we're not going to look at any of these. I have no idea what this is. Maybe it's one of those, diagrams where they in doctor's office. Maybe it's an elephant with a big ear. So what is a mathematical definition of a normal curve? Well, the mathematical definition of a normal curve in this case is 1 by square root of 2 pi e power minus half x minus mu by sigma whole square. If that sounds Greek to you, it should, because a lot of it is Greek. Okay. Now here's the question. So if I were to take this definition and draw the values, it will turn out to be exactly like this. Do you remember your calculus? If I ask you to find the area under the curve, what would you do? You would integrate your function between the limits. If you integrate this particular function between this value and this value, you will get this area. Fortunately for you, I gave you a table. So if you can look at a table, you don't have to do the integration. Okay? So that's what we're going to do. Now, take a look at the two things. Okay? Let's assume the value of mu is the same. Which one has greater spread? Which of the two density curves has greater spread? The one on the left. Obvious, correct? It's spread out a lot more. So bad for us. But we have to deal with it. So what does it tell you? In a normal distribution, greater the spread, the flatter the curve. Okay, that automatically falls into place. Spread or standard deviation is measured by this Greek letter, which is, very good, that is sigma. Now you probably know sigma as this, correct? This is uppercase sigma, this is lowercase sigma. I'm half Greek, by the way. I know the complete alphabet in Greek. My name in Greek means mad woman. Of course, in Indian it means madman, but that's a different. So here's the family of curves. So can you tell me the difference between these three curves? Essentially, they have the same spread. Therefore, the standard deviation is the same. The only difference is a measure of the center. All shifted. By the way, what would the medians be for those three curves? What can you tell me about the median? It would be the mean. Very good. So here is the property of the normal distribution. The mean and median are the same point. The normal distribution is perfectly symmetrical. Area to the left of the mean is equal to area to the right. And each area is equal to area to the left is equal to how much? 50%. Thank you. So each area is the same area. So basically, if you take the mean and split the normal distribution, the left-hand side is a mirror image of the right-hand side. Perfectly. Okay? So that's the normal distribution curve. So because of the symmetry, we don't even have to use the tables to come up with some answers. Okay? We can do it in a slightly different way. So here is a normal distribution. Here is the mean. If I go one standard deviation this way and one standard deviation this way, then the total area within one standard deviation of the mean is approximately 68%. You say, why is that interesting? Well, suppose I tell you that your exam scores on average was 72 with a standard deviation of 2. Okay? Average 72, standard deviation of 2. I can also tell you that your exam scores follow a normal distribution. I can immediately tell, without doing any calculations, without looking at the numbers, that 68% of the students had a score between 70 and 74. straight away. I don't have to do any calculation. So once you know that something is normal distribution, a lot of the properties are very well defined. Okay? So one standard deviation is 68%, two standard deviation is 95%, and three standard deviation is 99.7%. Have you ever heard people remarking, oh, he's more than three standard deviations above? So what does it tell you? If you're more than three standard deviations above, right here, 99.7, that means there's only 0.15% of people above your score. You might say 99.7 subtracted from 100%, that's 0.3. Why am I writing 0.15? Well, 0.15 on that side, 0.15 on this side. Agreed? So if you are more than three standard deviations above the mean, you are at 99.85 percentile. That's why it's so rare to find somebody more than three standard deviations above. Okay, so we know that. So the table I gave you is called the standard normal. It's called the standard normal distribution. That's the table I gave you. And the standard normal distribution has specific properties. First of all, the standard normal distribution is represented as n mu sigma. This is the mean. This is the standard deviation. So the standard normal is n01, where 0 is the mean and 1 is the standard deviation. So if 1 is the standard deviation, what is the variance? 1 also, because variance is the square of the standard deviation, and 1 squared is 1. So why do we want to study the standard normal? Well, think about this, right? If I gave you a normal distribution with mean 3 and standard deviation 5, and I told you to do a problem, you said, oh great, I know how to do this. You do it. Then I gave you another distribution with mean 7 and standard deviation 2, you do it. Then you'll say, where's the table for that? So for every normal distribution I give you, you come back with and say, where's the table for that? You know, there won't be enough trees in the world. So what we do is, you can do any distribution you want, okay, any normal distribution. I convert everything to the standard normal. And then, all I have to do is have one table for the standard normal to look it up. So how do I convert any normal distribution to the standard normal? Very simple. Just let me wipe this thing out. I'm going to take any distribution, normal distribution, to the standard normal as very simple. So in this case, I know that the mean is 64.5 and the standard deviation 2.5. So let's take a number 67. Okay? How do we do that? It's called standardization. I'll take the number 67, subtract from it the mean, which is 64.5, and divided by the standard deviation 2.5. What do you think I get? 1. So let me ask you this question. Look at this distribution right here. How far is 67 from 64.5 in terms of standard deviations? Exactly 1, right? So if I were to translate that to this, how far should this value translate onto this? This number right here. Exactly 1. You see it? So all these numbers are nothing but how far they are from the mean in terms of standard deviations on this scale. So because the standard deviation is 1, if you give me a number 2.5, I can tell you that number is 2.5 standard deviations from the mean. Very simple. So the standard normal, all it's doing is transforming any number you give to a curve that gives the value in terms of how many standard deviations it is away. Okay? So that's called the z-score. So let me give the transformation. This is your transformation. Take the value, subtract the mean, and divide it by the standard deviation.